You have stuff for me? Yeah, please.
Did you pass me? I should.
Registration that starts at 7, so I can't do it until like the 6th or so.
That's fair.
Okay. Who's taken their foreign language so far? Does it matter what language you say one in? Each, echad. I can count any language, right? Echad, shtayim, shalosh, arba, chamesh, sheva, shmona. Whatever language you want. Eins, zwei, drei, vier. What's 5 in German? Anybody know German enough to know 5? Fünf. Fünf. Thumb. Eins, zwei, drei, vier, fünf. Why do we count by tens? Because we've got them. The numbers are related to what we have. So when I think about the way I represent an integer, I'm really thinking about not just the word I use, but the symbols I use. An integer itself can be in anything. I don't care how you write it. If I run into an alien, they might not call them the same things we do. We're going to understand 1 and 2 in some fashion. Pick any integer bigger than 1, b, and any positive integer, then there's a unique expansion of n in base b. Now, what does that mean? It means I write n as some coefficient of b raised to the kth power plus some coefficient of b raised to the k minus first power, all the way down to a coefficient of b squared, a coefficient of b, and a coefficient of 1, which technically is b to the 0th. And k is the length of this number. Each of the a's is strictly smaller than b, but bigger than or equal to 0, and ak, this first one, is not 0. Somebody give me a 3-digit number. 232. You even said it, 232, in powers of 10. This is 2 hundreds, 30 is 3 tens, and 2 ones. But if I pick a different number for a base, I get a different idea. I'm going to write my base as a subscript. outside a set of parentheses around my number. Two, 3, 2, I can't use 130 anymore because I'm not in base 10. 2, 3, 2, base 6. What integer is this? Oh, it's 2, 3, 2, base 6, but I don't count in base 6. So to me, this is useless, isn't it? Let's convert it. What is the base 10 decimal equivalent of this number? Oh, I'm going to do the exact same expansion. Only instead of powers 10, the powers of 6. So I have 2 times 36 plus 3 times 6 plus 2 times 1. So that's 72 and 18 and 2, which is 92. Our, quote, normal numbers are automatically assumed to be in base 10. I don't bother to write a base for those. That's the typical decimal expansion we're working with. I can't do 2, 3, 2 if my base is 2. Why not? There's my definition of a base B expansion. If I'm using base 2, why can't I write 2, 3, 2 base 2? I know the answer is up there. Colin?
It has to be less than the 3 and 2 are greater than 3.
If I'm using base 2, I can't use any digit 2 or larger. If I'm working in base 6, I can't use any digit 6 or larger. I'm restricted to a particular set of digits based on my base. So the fact that I'm in base 2 means the only digits I'm allowed to use are 0 and 1. Hint. What did we call those back when we were doing the computer programming side of this game? That's the type of number I got. I got a binary number. But the actual zeros and ones were called, back in chapter 1, a bit. And a bit is short for binary digit. So convert this bit string, this binary number, into a base 10 integer. First thing I need to do is start counting. What's my power of k? 0, 1, 2, 3, 4, 5, 6, 7, 8. This is the 8th spot. Which means it's going to start 1 times 2 to the 8th. And then 0 times 2 to the 7th, 1 times 2 to the 6th, 0 times 2 to the 5th, 1 times 2 to the 4th, 1 times 2 cubed, 1 times 2 squared, 1 times 2 to the 1st, and 1 times 2 to the 0th. Okay, now I need my powers of 2. What's 2 to the 8th? You own calculators. You do not have to do this in your head. You can, but you don't have to. It's 256. 512 is 2 to the 9th. 2, 4, 8, 16, 32, 64, 128, 256. So that's a 256, nothing there. 64 there, nothing there. 16, 8, 4, 2, 1. Add them all up. Told you need your calculator.
$351.
351. There are a lot of commonly used bases that are powers of 2. Working in base 2, we already said earlier, we're going to call that binary. But we also frequently work in base 8. So we'll call that one octal. And base 16, hexadecimal. Hex and dec, 6 and 10. In the same way I do base 12, duodecimal. These are commonly used bases. Gee, why am I going to use base 12? There's another reason to use base 12. Base 12 is divisible by a lot of things. 1 and 2 and 3 and 4 and 6. And it's so the fractions in base 12 actually look really nice. I haven't talked about fractions yet. Base 12 was at one point considered a better base than base 10. So for the reason we still have dozens, right? 12s. Anybody know what a dozen is called? There's actually a word for a dozen, which would be the next slot, right? We'd have 1s and 12s and then, well, 1s, 10s, 100s. It's 1s, dozens. A dozen is a gross. These numbers got so popular that back in the 70s, in order to teach students who could really remember all of those rock and roll lyrics but couldn't remember the times tables, ABC ran a cartoon Saturday mornings in between other cartoon shows. They ran 2-minute cartoons called Schoolhouse Rock. Schoolhouse Rock included counting by 12s and working in base 12. And there's the video, little 12 toes. I wish I was making this up. It's really weird, though, because when I think of the numbers I'm going to write in base 12 or in base 16, I have a problem. My symbols, my A's, those are my digits, right? Well, I can't use a digit bigger than 6. I can't use a digit bigger than 2. But if I'm in duodecimal or hexadecimal, I have a digit no bigger than 12. Means I need a single symbol in base 12. So I need to think about the symbols I'm going to use. If I'm in base 12, I need 12 symbols. I got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I need 2 more symbols. Oh, crap. I can't use 10, 1, 0. That's not a single symbol. I need a symbol for the digit deck. for 10, right? Okay, dec. L for 11. But when I get to 12, 12 is that. That's 112 and no ones, right? So these are the numbers from 1 to 11, which means I can write the following as a number. That makes sense. I don't know how the hell you'd read it, but it makes sense. Well, technically, if I'm using the same abbreviations, that's 3dec 4L base 12. Yeah, that's just flows off the tongue so naturally. The hell is this number? Let's convert from duodecimal to decimal. This is, okay, again, I got to count places. 0, 1, 2, 3. This is 3 times 12 cubed plus dec times 12 squared plus 4 times 12 to the first plus L times 12 to the 0th. 12 cubed is 1,728. 12 squared is 144, and I get 10 of them. 12 to the first is just 12, and I get 11 ones, because that's 12 to the 0th. Out come the calculators. Yes? If I'm working in base 16, I need 16 different symbols. What am I going to do once I get past 9? I'll start using the alphabet. Which means this is a number. Cafe. That's absolutely a number. In base 16. Isn't that ridiculous? The symbols can be anything I want. For the record, the numbers you all recognize took about 300 years to get here. The current system of Arabic numerals started recognizably in the mid-1300s and did not evolve into these particular numerals that we know and, I hope, love until the late 1700s. Albrecht Dürer wrote one of the first typefaces that contained recognizable to us today numbers. So how do I get the decimal equivalent of this? Expand. Give me the decimal expansion equivalent to this hexadecimal number.
Do you want the letters or like?
Well, this is where you get to decide. You could go directly to this, or you could go and jump right to here. That's fine. I don't care, but the first line should be one of these two. Whether you're using the letters in there or the number is up to you. As long as you remember which letter is which number. That's the important part. So Evan, I'm assuming you mean like an expansion like this. I don't care if you write the letters down first, or if the first thing you do is convert them to their base 10 equivalents. So if I want to write C, A, F, and E here, I can, but I can also write 12, 10, 14, 15 here, and 14 here, right? That's perfectly acceptable. I just have to then remember to multiply out all the powers of 16. So this is 12 times 4096 and 10 times 256, 15 times 16, and 14 times 1. Is that right? 51,966. The larger your base is, the smaller the representation of any given integer. The smaller your base is, the longer the representation. I mean, consider the binary expansion of 351 was 9 bits long. That's not short, but the smaller my base, the bigger that's going to get. You'll notice we did not include a base of 1, because then the only digit you're allowed is a 0. And so your number is, how many zeros are there? Which is tally marks, isn't it, right? 1, 2 marks is 2, 3 marks is 3. That's useless. That's not a number, that's just counting. Questions? How do I go the other way? A number without any subscript, without any parentheses, is assumed to be indefinite, which means that's 111, not 111. I know what base that's in. What base do I want it in? 8. Base 8. How do I get there? All right, wait a second. I'm going to go back to elementary school and remember all of those manipulative things we had, right? You had little rods that were divided into 10 little cubes. You had 10 individual cubes. You had a big square that was 10 by 10. That was 100. And so I would say, oh, well, this is going to be one of those plates and one stick and one little loose square, right? Cube. 1, 1, and 1. But that groups by hundreds first. How many 8s are in that pile? How many 64s are in that pile? Oh. Uh-oh. I got a problem here. What I could do is I could say, oh, well, I know in base 8. In base 8, it's 8 to the 0, 8 to the 1, 8 to the 2, 8 to the 3, right? If I was counting this way, so these would be 1s and 8s and 64s, and then 128, 256, 512. Wait, that's too big, isn't it? So what I could do is I could say 111 is 164 with a bunch left over. What's left over? Say again? 47. And then I could say, well, okay, 47 is so many 8s with something left over, right? Because that's the next power down. Yes? How many?
5 8 plus 7.
And then 7 is just in terms of 1. Here are my digits, aren't they? 111 in decimal is 164, 5 8s, and 7 1s in base 8. Oh, I like that. There's just one problem. I have to know this list. I have to know powers of 8 until I get to a power of 8 that's bigger than my number. What if I ask you to do, I don't know, 372,413? I don't know powers of 8 that high. I'm in trouble. As much as I like this, the fact that it requires me to know these lists bothers me. Let's do this backwards. Let's not get the biggest digit first. Let's get the smallest digit first. Think about 111, right? Everything above the first digit, sorry, the rightmost digit, is going to be divisible by 8, isn't it? All of these powers of 8 have at least one 8 in them. This one doesn't have any 8s in it. So what if I write 111 as something times 8 with something left over? This is quotient and remainder. What's my quotient? What's my remainder? These were all quotient and remainder questions. So I've done this. What's 111 divided by 8? 13 point something, right? What's the something? If you've done the division on your calculator, you can read off the decimal to me,
875.
which is 7 eighths. Now take that 13. How many 8s in 13? With what left over? Now take this 1. How many 8s in 1? 0. With how many left over? From bottom to top, those remainders give me the digits I want. I had to divide by 8 twice to get to this 1, right? So I divided by 8 and then I divided by 8 again. Isn't that the same as dividing by 64? That's how many 64s it took. You sneaky mother. This method only required me to know one number, the base. So as long as I can divide by the base and get quotient and remainder, I'm done. $117,130 decimal. Let's move it to hex. Oh, I apologize. I did that without even thinking of it. A lot of calculators and a lot of old computer programs, instead of writing the subscript as a numeral, would write the word. So in binary, you'd see a string of ones and zeros, and instead of a subscript 2, you'd see the subscript BIN, binary. Or you'd see the subscript OCT, octal. For hexadecimal, you'd see HEX. By default, I think of it in hex. That's hexadecimal's abbreviation. As a joke, we got my father, who was a biomedical engineer programmer, a t-shirt that said hex 28, still great. What's 28 hex converted to decimal? $28 in hex. It's 2 16s and an 8. That's 32 and 8, that's 40. He got the t-shirt for a 40th birthday present. All right, if I want to go to hexadecimal, I'm going to do this quotient remainder, repeatedly dividing by 16. 117130 is something times 16 plus something. I need a quotient, I need a remainder.
7,320.
Say again?
7,320.16.
Okay, so take away the 7320, subtract it from the number you've got, and take the 0.6, whatever your answer is, multiply by 16. And you get 10, right? That's my remainder. Wait a minute. I need a single symbol. What should I write instead of 10? A. The rightmost digit of my number is A. Now I bring this number over. 7,320 is something times 16 plus something. Do the division again.
$82 and then plus 8. Wait, no, sorry, 1,300. Wait,
That's not the number I'm getting at all.
I just read it wrong.
7,320 divided by 16.
Is 82.5? Wait, no, I didn't know.
I'll agree with the 0.5. What's the quotient?
457.
Aha. The 0.5, therefore, is half of 16. Half of 16 is 8. That's my next digit. Now I repeat the process. 457 goes over here. How many 16s with what left over?
$28.
28 16s with 9 left over. There's my third from the right digit. 28 is so many 16s with something left over. Oh, 28 is 16 and 12. That's 1 16 with 12 left over. So what goes here? C. And then 1 is no 16s with 1 left over. That's my number. I have a clear algorithm and a clear halting condition. Remember our halting problem idea? I know this algorithm will eventually terminate when my quotient is 0. No matter what I'm converting from or to, this ends when I repeatedly divide. This ends when my quotient is 0. And then I read these in reverse. This is a really simple piece of code to write, people. A, 8, 9, C, 1, done. It's just one loop. Took all of 5 minutes to find the code. All of you CS people should be hunting furiously. Questions? Page 263. That was the old book, 263. In the new book, it is page 267. There you go. Quotient. Start with k being 0. Keep going. It spits out the remainder. And then I replace. So I have the new number I want to divide. Then I do the next division. I increment until I've gotten all of the digits out. However, I would point out to you that it is far less reasonable if I give you a number like this and say, I'd like this in binary. That's a really small base, right? So I'm going to get a lot of numbers, aren't I? But both octal and binary and hex are all powers of 2, aren't they? And that means that if I think about the numbers from 1 to 16 in decimal, actually, let me make it 0 to 15, because that's in hex. That's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. There it is in hex, right? But every number smaller than 16 is really 4 things that are powers of 2. Let's start all the way over here with 15. 15 is an 8, a 4, a 2, and a 1. 8 and 2, 4 and 1, that's 15. 1, 8, 1, 4, 1, 2, 1, 1. The digit F is equivalent in binary to the binary number 1, 1, 1, 1. The same thing with E, but it's an 8, a 4, a 2, and no ones, right? And I can do this all the way down. 12 is 8 and 4. When I'm down here, it's no 8s, 1, 4, no 2s, no 1s, right? All of these can be converted to binary. Octal only uses the numbers from 0 to 7 anyway, right? Right above the algorithm I showed you is a conversion chart that shows hexadecimal digits, their octal equivalents, and their binary equivalents. How does this benefit me? I just wrote down a number in hex, right? This number up here. One C98A in base 16. If I replace each of those individual digits in hex with their 4-bit binary equivalents, I've converted directly from hexadecimal to binary. 1 is 0001. C is 1100. 9 is 1001. Use the table on page 267. 8 is 1000. A is 1010. I don't have to go back and do this all over again in base 2. I don't have to do it in octal either, because in octal I can use that same chart. I can say, oh, in octal 1 is 01. What's C? Look at the table, page 267. This is 12, right? 12 is 8 and 4. 8 and 4. 1 8 and 1 4. Oh, that doesn't help. 9 is an 8 and a 1. 8 is 1 8 and 0. A is 10. Switching between hex and binary and octal is trivial with that table in front of me. That was the hint dropping as to something that should go on your formula sheet for exam 3. It's easier if I actually have the binary number. Let's consider this binary number. Where's my big binary number from earlier? La -da 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 -da. We did this one in decimal. What is this number? Blake? 350. This is 351. Now I could convert this from decimal to octal or from decimal to hex, right? But if I remember that 8 is 2 to the 3rd, I can take this number and write it in groups of 3, starting here on the right. 1 1 1, 1 1 0, 1 0 1. Kind of like I just put slashes every 3. I just put a little space in between them. Right? Like we put commas. Ready for the fun part? Do the switch. What is the octal for 111? Grab that table, or that's a 4, a 2, and a 1. That's 7. 0, 1, 1. 1, 0, 1. That's correct. If I want to do it in hexadecimal, 16 is 2 to the... What power of 2 gives me 16? So instead of breaking them up by 3s, I break them up by 4s. Converting back and forth between bases that are all powers of 2 is really, really nice. Questions? It doesn't matter how I write the number. Everything I do in arithmetic should still work. I hope this is not too hard of a question for you.
Is that 108 or 100?
100.
180 then.
Good. That's the same problem. Terrifying, isn't it? This was trivial. This looks insane. It's exactly the same thing. What's 1 plus 0? 1. What's 0 plus 0? 0. 1 plus 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 1 in binary is 2. Whenever I add and I get an answer that's bigger than my base, I move to the next number, right? What we're really doing is carrying. Two and 3 makes 5. 4 and 7 makes 11. So I put a 1 here and I carry the other 10. And 1 and 3 and 1 makes 5. But if I'm doing it in eighths, I should do the same thing. Oh, 107. I put the numbers in backwards. Let's fix that. 342 plus 173, both in base 8. 2 and 3 is 5, but 4 and 7 is in base 8. It's 11, but 11 is 1/8 with 3 left over. So I write down the 3 and carry the 8. And 8 and 1 and 8 and 3 and 1. I'm sorry, 1 and 3 and 1 is 5. Switching bases gives me a different representation of the answer. But they're equivalent answers. If I can carry, I can borrow. I get to go back and sing a song. Tom Lehrer, professor of mathematics, first at Harvard, then at UC Santa Barbara, gave up his teaching job at Harvard because he could make more money sitting at the bar singing silly songs. And recorded 3 albums of those funny songs, including one about subtraction and basic called New Man. We're going to do that subtraction problem on Monday. I will see you all on Friday for the exam. Have a wonderful rest of your day.